Hello YouTube! Today we will be going over systems of linear equations and how they relate to linear transformations. So the plan for today, for this video, step 1, we will introduce what systems of linear equations are. Then we will show that systems of linear equations can be viewed as linear transformations from these two spaces. Then we will link the number of equations and unknowns in our system of linear equations with the dimensions of our starting space and the dimension of our target space. Then, once we have established this link, we will be using the rank nullity theorem to establish a result that can tell us when a system of linear equations has a solutions just by looking at the number of equations and unknowns in the given system. So let's get to work. So step 1, what is a system of linear equations? Definition: a system of m linear equations in n unknowns is the following. So this collection over here, we got m equations and they are of this form, and here are our x's and unknowns. So all of these are elements of our field, so they're scalars. Now let's go from this and see how it relates to linear transformations. So, change of perspective. Observe that, let's take some linear equation from the system, so some ith equation. It is of this form. Now, so we can write that as this using just summation notice to make it a bit more compact. And if this can be viewed as a function, so I plug in x's, x1 all the way to xn, I plug in those, the scalars are already given, and then we just compute and we get a result. So this can be viewed as a function. And it turns out this is also a linear function. So it's a linear transformation from the space of all the ordered n tuples to just the space of scalars, because when you compute this, you just get a number at the end, just a scalar, whilst we're inputting these ordered lists of x's, n of them. So we've established that each of these linear equations can be viewed as a linear transformation. So now we will define this t, which takes in x's, to be the following. This ordered m tuple. So the first equation all the way to the mth equation. We put them in this list, and now we have a function that takes in, so when I plug in an x from the space of all the ordered n tuples, I plug it into the first equation, I get a number, and all the way to the nth equation we also get a number, and we store all of those numbers in this list. Now this t of x, so t, is a linear transformation from the space f to the nth to f to the mth. And now we have that this over here, so the linear transformation with its input x's, when we set it to some b, well, this is just a equal representation of our system of linear equations. So we can go back and forth. And now we have, since we've gone from systems of linear equations to linear transformations, now we can use some results relating to linear transformations to establish some results about systems of linear equations. So notice that the dimension of our starting space, f to the nth, is equal to n, and that's the number of unknowns in our system of linear equations. And the dimension of our target space, f to the mth, is, well, m, which is equal to the number of equations in our system of linear equations. So now let's apply some tools that we've established relating to linear transformations and see what we can derive. So let's find out if just knowing that, n is less than m, so the number of unknowns is less than the number of equations, or m less than n, so we have more equations than unknowns, we can conclude from just knowing whether one of these holds, we can conclude whether our system of linear equations, this, has a solution or not. So we will be first discussing the case where b is equal to 0. So this is a homogeneous system of linear equations. So now let's notice, if x is a solution of this system of linear equations, well then x gets mapped to 0. That means that x belongs to the null space of T. And vice versa, if x belongs to the null space of T, then x gets mapped to 0, so x is a solution of T of x equals to 0. So x is a solution of our system of linear equations, then x belongs to the null space. So if the null space of T is just the 0 vector, then this system of linear equations only has the trivial solution where x is equal to 0. So all the x's, all the way from x1 to xn, are just 0. Now, if the dimension of our null space is greater than 0, then our system actually has non-trivial solutions. And now let's relate this. So if the dimension of null t is greater than 0, then if you can recall, we know that t is not injective. T is only injective if the dimension of null t is equal to 0, if it's only this space. So now let's show that if the dimension of our target space is less than the dimension of our starting space, then t is not injective, which should make sense for if our starting space is of some dimension and the target space is of less dimension, so it's smaller, then t, when it maps, it obviously has to squish a v, so it has to, different vectors get mapped to the same thingy, so breaking the injectivity of t. Well, let's show that formally. So if t is a linear transformation from v to w, and the dimension of w is less than the dimension of v, then t is not injective. So using the rank nullity theorem, we can write this. We know that the dimension of null t is equal to the dimension of the starting space minus the dimension of range. Well, this is bigger or equal to than the dimension of v minus the dimension of w. So the dimension of range t is either less than or equal to than this, and when we multiply both sides of that inequality by minus, we get that minus dim range of t is greater than or equal to than minus dimension of w. So we have this inequality, and now since the dimension of w is strictly less than v, we know that this has to be greater than 0. So we get that the dimension of null t is greater than 0. Thus, null t is definitely not this. It's not equal to this vector space. So t is not injective. So now, in our case, since our t goes from f to the n to f to the mth, so if m, the number of equations, is less than n, the number of unknowns, then we can establish that t is not injective, meaning that our system of linear equations has non-trivial solutions. So if we have if the number of equations is less than the number of unknowns in a system of linear equations of the form this, so a homogeneous system of linear equations, then there exist non-trivial solutions. Now let's look at this case. Let's look at when our system of linear equations is of this form, where b is not equal to 0. So at least one of the b1, b2, all the way to bm, at least one of them is different from 0. So thus, for every choice of non-zero b belonging to f to the m, exists some x in f to the n, such that t of x is equal to b. Rephrased, does the range of t equal the target space f to the mth? So, which is also equivalent to saying, in this case asking, is t surjective onto? Well, let's show this result, that if t is a linear transformation from v to w, and the dimension of our starting space is less than the dimension of our target space, well then t has no way of being surjective, that is onto, for linear transformations either just preserve the dimensionality of our starting space or they lower it. So if the target space is greater, then t should have no way of being surjective. So let's prove that. The dimension of range t, again using the rank nullity theorem, we express this dimension of this space as equal to the dimension of our starting space minus the dimension of the null space. While this, so we know that dimension of w is strictly bigger than this, so we have this, and we we're either gonna have 0 here or some number. So this is definitely gonna be less than or equal to than the dimension of v. So that means that this whole thingy is strictly less than the dimension of w. So we have that the dimension of range t is less than the dimension of w, meaning that t is not surjective. There is no way for t to be surjective. So translating again to our system of linear equations, we have that if the number of unknowns is less than the number of equations, then this system over here, where again b is strictly different from 0, it has no solution for some choice of b. So if this is the case, there exists some b, at least one of it, that there is no x that gets mapped to it. So if a system of linear equations of the form this, non-homogeneous, tx equals b, has more equations than unknowns, then the system doesn't have a solution for some b. So yeah, that would be it. So we went from systems of linear equations to linear transformations, and then using the rank nullity theorem, we established some pretty nice results relating to whether a specific system has a solution or not. So here we go. Outro. So if you find that my content has some semblance of value and want more of it, please consider, liking the video and or subscribing and or commenting. All of this helps. So yeah, in the next video, we will be introducing the infamous matrices. So introducing the matrix of a linear map. Yeah, till then, wish you all the best.